Hi student, this video is to explain the processor execution of a given program consisting of multiple lines of instructions. First, you need to understand that a program consists of instructions. So when a program is executed, each instruction is actually experience instruction cycles. For example, if there are 3 instructions, then the execution actually consists of 3 instruction cycles, each instruction cycle for each instruction. So what is instruction cycle? It's a cycle that the CPU processes an instruction. It generally consists of 3 subcycles, which are fetch subcycles, indirect or operand fetch subcycle, and execute subcycle. So it depends on the architecture and design of the processor. So the example I'm using here is that one instruction cycle consisting of 3 subcycles as illustrated in this slide. For each subcycle, it actually consists of multiple of micro instruction. So for example, fetch subcycle, when performing fetch subcycle in the processor for a given instruction, actually it is done through one or more micro instruction. So in this example, it shows that one fetch subcycle actually is done using 3 micro instructions. So what is micro instruction? So as the figure shows here, micro instruction is the refinement on the components, the elements of an instruction. So one micro instruction actually consists of one micro instruction represent one or more micro operation. So fetch subcycle is done using, say for example, 3 micro instruction, 3 different micro instruction to realize the fetch subcycle, and each of them consists of different micro operation. Some of them just one micro operation, but some may be more than one, like this. And micro operation is the most basic or the atomic operation in the CPU. So it could be the transfer of the data between the registers, the transfer of the data between register and memory, or it could be the execution of the arithmetic logical unit, like what would happen under the execute subcycle. So let me use this diagram again with using the example program. So if you have 3 lines in this program, exchange followed by sub instruction followed by jump. So when we execute these 3 lines or 3 instructions in a program using a CPU, so CPU run this execution through 3 instruction cycles. So one for each instruction. For instance, the first instruction cycle is run for the exchange, the first line, and so on. And under the instruction cycle, there are subcycles. Under the subcycles, there are micro instructions, and under each micro instruction, there are micro operations, as explained just now. So after executing the first line, when moving to the second line, which is sub instruction, then it is done through the second instruction cycle, which consists of the subcycles, the micro instructions, and the micro operations. The same goes to the third line of the instruction. In this case, it is jump, and in some instruction does not have the indirect cycle. Okay, because fetch means fetching the instructions. So every line of the instruction need the fetch subcycle, because the CPU need to first fetch the instruction, then only can run it through using the components in the CPU. But the second subcycle shown just now is the indirect or operand fetch. Some of the instruction doesn't need operand fetch, or either through direct addressing or indirect addressing, like jump. So there is no need to fetch the operand. So we can the CPU will skip the indirect or operand fetch subcycle. So in this instruction, the CPU will only need to perform fetch subcycle with the micro instruction and micro operation, and followed by execute subcycle, which consists of the micro instructions and micro operations. Okay, now I will explain again the CPU execution of a given example program, but this time with the table that show what happened or what micro operation is performed for each clock cycle. But before that, we need to make an assumption what processor we are using. So let's in this example use a hypothetical computer to run the program. So the hypothetical computer is just a simplified processor that has all the important registers to enable the basic execution of the CPU. So the important registers are, by the way, register is a storage unit that temporarily hold the address or data or instruction that are used by the CPU. So the first important register is PC, program counter, that hold the next instruction address that need to be fetched by the processor. The MAR is memory address register that normally hold the memory address to be sent to the address bus, which is part of the system bus, so that the system can, based on the address, to get the content of the memory located at that address. Okay. IR is the instruction register, so which normally hold the instructions that are fetched from the memory, while MBR is the memory buffer register that temporarily hold whatever data that come from the memory, such as the operand to be used by the execution unit or the instruction that need to be sent to the instruction register from the memory. Other registers are the general purpose registers such as AX, BX, and CX. Apart from registers, we have control unit. Control unit issue the control signals to the bus or to the components inside the CPU to do some functions, for example, to control the data flow, which means the data flow from which register to which register. Besides that, the control unit also issue the control signal to control the functional mode of the execution unit. So, for example, this instruction require the function of addition. Then control unit will issue the corresponding control signal such that execution unit will function as the adder, and so on. Other unit, as mentioned, is execution unit. That is the important component for the execute subcycle. So what kind of function to be executed by the execution unit is based on the instruction. So now let me use this example hypothetical machine to explain again what happened inside the processor for each subcycle. So first, let's look at the fetch subcycle. So as you can see in the chart just now, each subcycle consists of micro instructions, and micro instruction is actually made up of the micro operation. So this fetch subcycle for this simplified machine consists of 3 micro instructions. Okay. So the first micro instruction is labeled as T1. Okay. The second micro instruction is T2, labeled as T2, and the third micro instruction in this fetch subcycle is IR, getting the data from MBR. So each micro instruction normally just spend 1 clock cycle to perform the operations inside the micro instruction. So like the first micro instruction is transferring the program counter content to the memory address register. Okay. So this is performed, the data transfer is performed in 1 clock cycle. Okay. And the second micro instruction here is actually consisting of 2 micro operations. Okay. So, and these 2 micro operations performed in parallel, because as I mentioned just now, if a set of micro operations belong to the same micro instruction, they are performed in the same clock cycle. So in other words, the data transfer from memory location MAR to MBR is done in parallel with incrementing the PC or program counter value. The third micro operation is transferring the data from memory buffer register to the instruction register. This also is performed in 1 clock cycle. So the fetch subcycle actually consists of 3 micro instructions, and it will spend 3 clock cycles to do it. Yeah? The first clock cycle, the second clock cycle, which consists of parallel micro operations, and the third clock cycle. So if we look at the subcycles, using this chart again. So what happened is, okay, just now I mentioned 3 micro instructions. So they are here. The first one representing by the first micro instruction under fetch, the second which consists of 2 micro operation, and the third which consists of 1 micro operation. And they are performed in the sequence, right? From the first micro instruction, the first clock cycle, the second clock cycle, and the third clock cycle. Okay, now let's look back at the structure of the hypothetical machine, and let's see what happened in the processor for each micro operation. And you also need to take note of the purpose of each micro operation related to the fetch. Okay. So first, the first micro operation that happened under fetch subcycle. As you know, fetch is to get the instruction from the memory to the instruction register so that CPU can interpret the instruction and do the necessary operation. That's why the first micro operation that will happen under fetch is transferring or copying the program counter to the MAR. So like shown in this red arrow, copying the instruction address to the memory address register. Because the instructions that need to be fetched from the CPU will be staying in the memory. So the PC need to tell the MAR where in the memory to get the instruction. So the control unit role is to issue the control signal read to the control bus so that the memory knows it is actually a CPU reading from the memory, not writing. Okay. So when PC copying past the program counter or the instruction address, the first instruction address to the MAR, to the address bus, so this address will keep moving to the memory, and the memory will know what location is being requested by the CPU to get the instruction. Okay. Then next, what happened is these two micro operation in the second clock cycle under the fetch subcycle. So after the memory is informed which operation to be sent out to the CPU, then the memory, okay, the MAR means the memory content located at that PC address will be sent out to the data bus, and then from the data bus it will reach MBR, because MBR function is to temporarily hold whatever data or instruction coming from the memory. Okay. And this is represented by this coming from memory located at the MBR, the PC, then passed to the instruction from there will be passed to the MBR. At the same time, the control unit will inform the PC to do increment by 1, because after fetching the first instruction, PC need to get ready for the second instruction in the next instruction cycle. Just get ready now, not going to fetch soon, but get ready the PC to the next value, which is by incrementing it by 1. Okay, so now the instruction is at MBR after the second micro instruction performed. The third micro instruction is to keep moving the instruction to the right place, which is the instruction register, so that the control unit can interpret what instruction is it, and then the control unit can issue the control signal to the right components to do the jobs based on the instruction. Okay, now let's move to the second subcycle. Okay, so just now is the first subcycle, which is fetch. The second subcycle we call indirect or operand fetch. Okay, so after the instruction is sent to the CPU will decode or interpret the instruction. So if the instruction need the CPU to fetch the operand, it could be using the direct addressing we have learned previously, or indirect addressing. So if it is just direct addressing, then it will involve 2 micro instructions here, T1 and T2. So only 2 clock cycles involved. However, if it involves indirect addressing, which will need to visit the memory twice to get the effective address for the operand, then the third micro instruction will be involved. Now let's look at the first micro instruction. What happened in the first micro instruction is actually after the instruction reach the IR in the fetch subcycle, so the control unit will interpret and then get the portion of the IR, which is the operand or address portion from the instruction, to be sent to the MAR, because that information is to tell where in the memory to fetch the operand for that instruction. So similar thing will happen. So the address in the MAR, this time is the address for the operand, okay, will be sent to the address bus, and then through the address bus to the memory to tell the memory that, okay, control unit also tell the memory that CPU need to read the operand from that address given in MAR. In case for indirect, then this step actually is to get the first address from the memory instead of operand. In case of direct, then it is getting the operand based on the memory in MAR. Next. So the second micro instruction shows that the operand, okay, in the case of direct addressing, the operand will be sent to the data bus, and then from data bus, it will reach the MBR register. Okay, that is the operand. And the operand is ready now to be used for the execute subcycle. But as mentioned just now, in case it is indirect addressing, what reach here is not operand yet, is the effective address to get the operand, and this effective address need to go through the instruction register so that the CPU can decode again actually where is the final destination in memory. The CPU need to get the operand to be used in the case of indirect addressing. So in this case, the address will need to go through the MAR again so that it can, this is the second time the system visit the memory, but this time because of indirect addressing, the second visit will get the operand to be used by the CPU for the execution. Okay, now let's move to the third subcycle, which is called execute subcycle. But execute subcycle is different for different instructions. So now let's take an example that the instruction in this instruction cycle is this. So the execute subcycle will involve just because the instruction just need to move a data from a memory to the register. So after fetch subcycle and operand fetch subcycle, the num value should have arrived at the MBR. And when come to the execute subcycle, it just need to transfer the num value to the general purpose register AX. Okay, so this is the execution in the execute subcycle for move. Okay. So as mentioned, execute subcycle is not fixed for every instruction. So it varies according to the instruction for that instruction cycle. So in the case of add the AX with the data coming from address 2400. So after the fetch subcycle and operand fetch subcycle, the value coming from 2400 should have arrived the MBR. So when entering the execute subcycle, the MBR value just need to be added with the AX value, and the result is stored in the AX value. Okay. Now, I will explain again what happened for fetch, indirect, and execute subcycles, but using the short 3-line programs. And another thing is we will use this table that has the information of clock cycles starting from T0, T1, and so on, to show that what is the change happened to the important registers for every micro operation. So here it is an analysis to show that the correct sequence of micro operation happening, okay, from T0 and so on, based on the fetch, indirect, and execute subcycles. And for each micro operation, what change has happened to the important registers of this simplified machine. Okay, now let's make some assumption. So this is a 3-lines program: exchange followed by sub followed by jump, and here next to each instruction, we show you the hex or machine code of the instruction, because what's stored in the instruction memory is the machine code of the instruction. Okay? Besides, then we will continue continue the table to show the register changes with the micro operations happening for the second instruction, and each instruction consists of fetch, indirect, execute. Sub also consists of fetch, indirect, execute. So you need to list down the correct sequence of the micro operation and the changes that happen to the register. Okay, same goes to the third instruction, but third instruction doesn't consist of the indirect operand fetch subcycle as mentioned. Okay, now let's start with the first instruction, exchange CX and num. So when running exchange CX and with num in the processor, okay, exchange this instruction means we exchange the value of CX with the num, or we swap the value between CX and num. Okay, so what happened in the processor, we need to follow the fetch, indirect, execute sequence, and for each subcycle we follow the micro operations listed there. Okay, so also other thing we need to assume is, let's assume initial value for num is 100 stored in the memory, okay, at this location 450, address 450, num is stored here and the value is 100, and at address 451 val1 is stored here and the address and the value is 500, and initially register CX is holding 200. So all this initial value will be given, and in this case we need to list this initial value in the first row of the table. So as mentioned just now, the each instruction has the hex code or machine code as listed here. So when you run a program, the program composed of the instruction will be first loaded in the memory. Okay? So the example of it as shown here, and each line of the instruction will have the address in the memory where the line is stored. For example, exchange with hex code A450 is stored at the address 39D, and the second instruction at 39E, and so on. Okay. And the first row of the table is just to show the initial value of the registers. Okay, so if it is unknown initially, you can leave them blank as shown here. Okay. So initially the PC is supposed to hold 390. Why? Because that is the address pointing to the first line of the instruction that will be fetched soon when the program is executed. So initial value for PC is 390. Next, at T1, then you start to analyze using the first micro operation under the fetch subcycle. So remember, there are 3 micro instruction or 4 micro operation under fetch. Okay. Now the first one is MAR. Okay, PC transfer the instruction address to MAR. So right here, okay, and then at the same time the set or update the register content based on the micro operation. So this micro operation state that the PC value will be passed to MAR, then the 390 in PC will be passed to MAR in this clock cycle. So the next micro operation is this pair. Okay, just right here this pair, and the first micro operation is getting the content of the memory at this address. What is this address? So this address you refer to the previous line is 390. So the address at 390 has this content. So this content A450 will be transferred to MBR. So you write the MBR A450. Okay, in the same clock cycle, we increment the PC to get ready the processor for the next instruction cycle. So the A450, that represent the exchange instruction, will be by the end of T2, okay, will reach MBR as shown by this table and animated in this diagram. Okay, then the third micro instruction is to transfer the instruction exchange to IR. Why IR? Because instruction register is the place where instruction will be decoded or interpreted by the processor through the control unit. So after this micro operation, then now the instruction in hex is now at IR register. So when it reaches IR register, IR is split into 2 fields. One field representing the opcode, what kind of instruction is it? In this case, it's exchange. And the second field is the operand or the address. Okay. So in this case is the 450, the address to get the operand. Now let's move to we have finished the fetch cycle. Now let's move to the indirect and operand fetch cycle, the second cycle. So as the instruction tell here, this is a direct addressing. Okay, so because the num directly tell the processor where to get the operand. Okay, so this is not the indirect. So the third micro operation will not be involved in this analysis. So we only take these two. Okay. So in the operand fetch, the operand portion of the instruction will tell where to get the operand. That's why only this portion address will be passed to MAR. Okay, so you can update MAR to become 450. So you see here is not A450, only the address portion of the instruction. So why it go to MAR? Because you need to go to the memory to tell which location, which is 450 in this case, to get the operand. And that happened in the second micro operation, where the content at the MAR, the content at the 450 will be sent out through the bus to the MBR. That is what happened in the operand fetch. Now the operand 100 is successfully fetched. And 100 actually is represented by this symbol now. 100 is successfully fetched after the second subcycle. Now let's look at the execute subcycle. So this is the swapping instruction. So different processor may spend different clock cycle for swapping. So here you are supposed to tell that swapping in this processor need 2 clock cycle. So T1, T2 will just be spent for the CX value go to MBR, MBR go to CX. So in this table, you take out 2 rows to represent 2 clock cycle, and then the CX and the MBR value are swapped in this 2 clock cycle. Where originally CX is 200, now it become 100 because the 100 coming from MBR. Whereas the MBR become 200, which is swapped from the CX. Okay, it is not finished yet because after swapping between CX and MBR, the temporary register MBR need to send back the swap value 200 to the destination, which is num. Because if you look at this exchange instruction, it is swapping between CX and num, not MBR. But num is in memory, which is far away. So normally what happens is the swapping will be done within the processor first, then only the value that is supposed to go to memory will be sent there in the next clock cycle. So first swapping is done between the MBR and CX, and then the temporary register MBR 200 will be sent to the location of num. So this will take out another clock cycle. So with this, you will see that 8 clock cycles has been spent just to execute one instruction. Okay, right? So if you assume in one instruction 1 clock cycle, then you need to correct your concept because as mentioned and illustrated in the chart just now, one instruction cycle consists of 3 subcycles, and then each subcycle consists of several micro instructions, and each micro instruction will take up 1 clock cycle. That's why you see totally in this case 8 clock cycles are required just for one instruction. So this is not finished yet because we have just completed the analysis for the first clock cycle. So if you continue to the second clock cycle, similar set of micro operations are considered here. Okay, and you continue with the fetch right away, fetch for the second instruction, which is sub. Okay. So the first micro operation will pass the 39E to MAR, okay, as stated here, and then the second micro operation will take the instruction at 39E to the MBR. At the same time, we increment the PC value for the next instruction cycle. Then finally, in the fetch subcycle, we pass the B451 hex value that represents the sub instruction to the instruction register. When entering the second subcycle, again you see this instruction is again the direct addressing, so we are not using the last micro operation here because it is not indirect addressing, it's a direct. Okay, so what happened is these 2 micro operations basically just to fetch the operand for the sub. The operand need to be fetched is the value from val 1. Okay, so what will happen first is the CPU will take the information of the address, okay, the location of the val 1, okay, to the MAR. And then MAR will send the address to the memory to tell the memory, please bring out the content at the MAR there, which is the content at the 451, and send to the MBR. Okay, send to the MBR. So now by right, the 500 override this old value. Now 500 take over the MBR. Okay, as mentioned in this table. Okay, so when executing, the execution is about subtraction. So you see the execute micro operation here is different from the previous exchange micro operation because as mentioned, the skip subcycle have the micro operation varying based on the instruction, the nature of the instruction. and in this case it is subtraction. So the 500 value coming from while 1 will be minus with the cx value. Okay? So MBR will be minus with cx and then store in MBR temporarily, because later this value will need to be sent back to the destination in the memory var 1. That's why we need the next micro operation here to send back the subtraction result to var 1. Okay, so first the subtraction happened and the result will be updated at MBR. Okay, and then the result will then send back to the location of 451 to replace the previous value of none. Okay, that complete the execution for the second instruction. Okay, now we move to the last one, jump. So as the jump instruction show here, there's no need to fetch the operand, so you don't need the second subcycle. So we only need fetch and execute. So same set of instructions, same set of micro operation we need for fetch. First, the PC value will be passed to the MAR so that the address 39F will reach memory to ask memory to send out the instruction C39D representing jump to the MBR. That's why in the table C39D is updated in the MBR, and at the same clock cycle it is the PC is incremented by 1. Then the instruction C39D in the next clock cycle will reach instruction register. So as mentioned, there is no operand fetch in this case based on the jump instruction. So the next thing that will happen is to execute subcycle, where it is for jump, it is to update the PC value based on the jump target address, which is L1. Okay? So the target address is 390 because the jump L1 mean in this instruction, after the third line of the instruction, it will need to jump back to exchange, and you know exchange location is 390. So also as stated in the as the target address of the jump instruction. So this 390 will be updated to the PC value, so that the next instruction to be fetched is the exchange instruction. Okay, so with that, I hope you can see that when a simple program is executed in the CPU, it actually involves not only one clock cycle, but multiple clock cycle, because one instruction cycle consists of fetch subcycle, indirect or operand fetch subcycle, and execute subcycle. And each subcycle consists of a set of micro operations. So totally it will take up multiple of clock cycles. So as in this example, 19 clock cycles are spent just for the 3-line instructions. Okay. So I hope this example and video help you to understand better about CPU execution. Thank you.